Okay. Thank you for that introduction. So today I'm going to be presenting my Master of Science research titled Prolonged Post-Orogenic Extension in the Southeastern Canadian Cordillera, Miocene Reactivation of the Columbia River Fault. Based off Noah's introduction, as you know, I did my Master of Science at the University of Calgary, and that is what this research is from. So let's see. There we go. I guess a little bit about me, not as necessary. I went to the University of Calgary for my bachelor's and master's starting in 2016, and I started doing research in thermochronology with Dr. Ava Ankelman starting in 2018 in my second year of my undergrad. I carried that research through for a bachelor's science thesis, which then grew into my master's thesis that I expanded on. And then we published a manuscript on this research just earlier this year in Tectonophysics that you can go find. And like you said, I'm now working in mineral exploration as an exploration geologist. So getting into the research itself, this project is focusing on the Southern Canadian Cordillera. The Canadian Cordillera is just the Canadian portion of the much larger North American Cordillera, which is the mountain belt which stretches along the western margin of North America from Alaska to Mexico. In Canada, in southern Canada, this portion, the mountain belt was built during a period of accretionary mountain building from the Jurassic to the Paleocene, and it comprises rocks from the ancestral continental margin from the Proterozoic to the Paleozoic, followed by accreted terrains which formed both close to and distally from the North American margin, which were accreted and deformed, as well as deforming the platformal sediments. So the mountain building led to the formation of 5 distinct morphogeological belts in the Cordillera. These are denoted by the different colors on this map here. From east to west, these are known as the Foreland Belt, the Amanica Belt, the Intermontane Belt, the Coast Belt, and finally, the Insular Belt. The belts we're going to be focusing on in this study are going to be the Foreland Belt, but most primarily the Amanica Belt. The Foreland Belt is also known as the Foreland Fold and Thrust Belt. These comprise the unmetamorphosed continental margin sediments that were deformed during mountain building. And then the Amanica Belt is the metamorphosed platformal sediments that were deformed, as well as that were intruded during mountain building. The Amanica Belt kind of represents the hinterland of this origin. It was like the first center of crustal thickening and metamorphism during mountain building. And it is a very interesting feature because it was also overprinted by Eocene post-orogenic extension, which led to the formation of this massive tectonic feature known as the shoe swap domain, which is high-grade metamorphic rocks bounded by outwardly dipping brittle ductile normal faults, as you can see here. So let's actually just go back. The important difference between the Foreland Belt and the Amanica Belt is that they're separated by this Rocky Mountain Trench, which is a prominent geographic feature, but also a very prominent lithospheric feature. So across this Rocky Mountain Trench, between the Foreland Belt on the east and the Amanica Belt on the west, we have a dramatic decrease in lithospheric thickness from being over 200 kilometers thick in the east to less than 50 kilometers thick in the west. There's different ideas as to why we have this thin lithosphere now between delamination or back arc thinning from mantle erosion. But what's important here is that we have the existence of a very thin lithosphere in the Cordillera and a sharp boundary below this Rocky Mountain Trench. So this present-day model kind of just shows that. This is a interpreted model, but this is based off of these high velocity zones from the subducting slab to delaminated lithosphere and the cratonic block, and then a low velocity zone right below the Cordillera, as well as high heat flow throughout the Cordilleran crust. So looking a little closer at the Southeastern Cordillera in this shoe swap domain, here you can kind of see it outlined in more detail. The shoe swap domain is a culmination of multiple metamorphic core complexes, each bounded by their own, normal faults. These high-grade metamorphic rocks are denoted in the lightish gray here on the map. Most of these bounding faults are trending about north-south on average, and the metamorphic rocks were rapidly exhumed and cooled between the Paleocene and the Eocene based off of geo and thermochronology studies. which suggests that it was rapidly cooled from 60 to 40 million years ago. The timing varies slightly throughout the domain based off of the individual complex you're in, but they all fit within this nice the Eocene window. As to why this extension occurred and the exhumation of metamorphic core complexes occurred, one model is that the Amanika belt was this over-thickened orogenic wedge as the hinterland of the origin, and once compression stopped after the Cretaceous, this large gravitational anomaly produced from crustal thickening was allowed to relax and led to lateral extension in the upper crust and the exhumation of mid to lower crustal rocks, which we see as these metamorphic core complexes. However, so this process of extension has been proposed to only go until about 40 million years ago. That is based off of thermochronology through the area. However, there are some studies that may put this into question. For example, there are tilted Oligocene and Miocene sediments near the Rocky Mountain Trench that are bounded by extensional faults, indicating there may have been more fault movement leading to extensional basin formation. Furthermore, structural analysis of major Eocene extensional faults indicates that there is an overprinting strike slip, potentially oblique slip component, post-dating this Eocene extensional episode. And then a thermochronology study from the northern tip of the Shuswap domain from the geothermochronology research group at University of Calgary shows that there was cooling west of the Rocky Mountain Trench, and that this may have been aided by the existing gravitational anomaly, which is present in the Columbia Mountains and the Rocky Mountains. So we now have, there's geologic evidence from Miocene lake strata, there is structural evidence from reactivated faulting, and there's thermochronologic evidence that there has been more recent fault motion and cooling post-dating Eocene. So how extensive is this? Has it occurred elsewhere in the southeastern Cordillera, or are these very isolated events? So to do this, we are zooming to the northern Shuswap domain specifically to do another thermochronology study and investigate what the timing of the most recent motion on these extensional faults was. We are going to be looking at a complex called the Monashee complex, and in this map here, it's denoted by the purple. It is a culmination of two migmatitic gneiss domes, known as the Frenchman's Cap, FC on the north, and the Thor Odin Dome, TO, in the south. The Monashee complex is bounded by a major Eocene normofault called the Columbia River Fault on its eastern boundary. This is going to be the highlight of the study and what we're going to be focusing on moving forward. Noting this Columbia River Fault, it is also the eastern boundary of the Shuswap domain at this latitude. So to the east, we have low-grade to unmetamorphosed accreted sediments, and then on the west side, we have these high-grade metamorphic rocks in the footwall in the metamorphic core complex. In yellow on the map are the locations of previous thermochronology samples and what the current, I guess, tectonic model for the area was based off of, which record cooling between 56 and 40 million years ago, and we are adding these blue samples onto it. Now, I would like to note, just from being able to see them all, there is not much spatial correlation as to where these samples were chosen. Our samples, as you'll see, and I'll explain, are sampled in a, a localized elevation profile so that we can correlate between samples, whereas a lot of these, sorry, not up here, but mostly just south along all these yellow dots, they were not sampled in a fashion to be correlatable between each other, so they're somewhat more sporadic, and that'll lead into our discussion later. Okay, so moving on, Monashee complex. We have this major normal fault on the east. To get a better understanding of what the geology looks like, here's a simplified cross-section. So in this area, we have divided the geology into three thermotectonic units, the upper, middle, and lower units. You can see the little legend here. So the Columbia River Fault is exhuming these high-grade metamorphic rocks from the lower unit and the middle unit and juxtaposing them against the lesser metamorphosed rocks of the upper unit. It is worth noting that in this area, the Columbia River Fault is different from other detachment faults in that it does not separate the middle unit from the upper unit. It separates the lower unit from the upper unit. So this middle unit that is in existence to the west of the major complex in dark green here, it is not present in the west on the east and along the Columbia River Fault. And this may be due to late brittle reactivation of the Columbia River Fault, further displacing these blocks and essentially just moving the middle unit from exposure. So this east dip in Columbia River Fault, that's where we're moving forward from. More detailed geology from our study area. So this is now the area where we have collected our samples, as you can see in blue. This is just north of Revelstoke along the river valley. And we collected samples in 2 elevation profiles, one in the footwall and one in the hanging wall, as well as grabbing a couple other samples just along strike of the fault at the valley bottom. So here you can see the east block, our hanging wall. It's known as the Clacnicuden complex. It's correlated to the upper unit because it has a metamorphic and cooling history much more similar to other accreted rocks in the area. And then the footwall, we have our Monashee complex, which includes the Neoproterozoic to Paleozoic paleo paranices, and then a Monashee core of orthonices and migmatites. So our sampling approach, we took samples along 2 elevation profiles on either side of the fault to investigate how cooling can differ at high elevation to low elevation along these fault blocks. Each profile covered about 1,000 to 1,500 meters of elevation, and we targeted exposed outcrops of metamorphic and granitic bedrock in order to get better apatite yields. For thermochronology, we want to understand what the cooling history of rocks in the area is. So that is exactly what thermochronology is for. Thermotemperature chronology to study time. To understand this simply, it's we have a premise known as a closure temperature in geo and thermochronology. And essentially what this is that above a certain temperature, radiogenic daughter products cannot accumulate in the crystal. Whereas below a temperature, radiogenic daughter products can accumulate in the crystal. So once you begin to accumulate your daughter, you can calculate an age since that system was closed, allowing those daughters to accumulate based off of the decay rate of their parent. Thermochronology, it's not that straightforward. In reality, we don't have a single closure temperature, but we have temperature sensitivity windows. And we can choose these temperature sensitivity window we want based off of a wide variety of thermochronometers. Since we want to investigate the lowest temperature history of these rocks to investigate the most recent faulting, we're going to use low temperature thermochronometers. Particularly apatite helium and apatite fission track. So the apatite helium has a temperature sensitivity window of 80 to 40 degrees Celsius, whereas the apatite fission track has a temperature sensitivity window of 120 to 60 degrees Celsius. Now for helium, this is known as the partial retention zone, as in the partial retention of radiogenic helium atoms. And the fission track has a partial annealing zone where fission tracks will be healing or annealing inside that temperature window. And these fission track and healing or annealing can be used as thermal history information for modeling and such. So in order to do apatite thermochronology, we need apatites. So I mentioned that we targeted igneous and metamorphic bedrock because they tend to have higher apatite yields. So we get their bedrock of about 5 to 10 kilograms, crush it up, and we get a bunch of little apatite crystals that we then pick through. I picked the very best that I can find for apatite helium, which were individually digested and measured in a mass spectrometer. And then for apatite fission track, you got as many apatites as we could find, polished them up, and I counted them on a microscope. Once we had the age data from those methods, I inputted into a thermal history modeling software known as QTQT, which allowed me to put together some inverse thermal history models. So essentially this program plots a time temperature history and compares how that time temperature history would fit to our observed data. Any histories that are within a acceptable fit to our observed data are then plotted as a potential path. Now, this QTQT program uses a Markov chain Monte Carlo, so it's kind of like a self-learning system, and it produces these models. The other the most important pro to using QD is I can input multiple samples from different elevations into a single thermal history model. So instead of treating each individual sample like a point in space that has had its own thermal history, we can now put these points in space and treat this as a fault block, moving how a fault block's temperature changes through history rather than individual points. And this is much better for interpreting how rocks across the elevation are related to each other. All right, so moving on to the actual results of what we have here. I've got all the ages plotted. The black are the helium ages and the blue are the apatite fission track ages. Note that the blue points are my samples and these yellow points are previous thermochronology samples taken in other studies. This orange sample is a potassium feldspar age from another study as well. So what we got from the helium is ages vary between the Oligocene and the Miocene, as well as the fission track also range from the Oligocene to the Miocene. There's a much wider range in the helium ages than the fission track ages. But overall, the single grain dates in each sample they behaved very well in each sample. Only 2 samples yielded a single grain date dispersion over 25%, meaning we couldn't derive a single mean age for that sample. So an age range instead is reported, as you can see here and here. Anyway, so ages behaved relatively well, except for those at lower elevations. Looking at how ages compare between the footwall and the hanging wall, in a cross-sectional view here, we have the Columbia River Fault just cutting these 2 blocks. So this on the left is the Monashee complex, the footwall, and then the upper unit, the hanging wall on the right. In the footwall, the ages are relatively similar. We have in blue, we have the helium ages, and in yellow, we have the fission track ages. So in the footwall, there's not much difference between the ages, whereas in the hanging wall, you can see a correlation between elevation and age, where decreasing elevation results in a decreasing age. There's also some more age dispersion found in these hanging wall samples compared to the footwall samples, where there's a bit tighter spread on those ages. So plotting these on an age elevation plot to investigate how these ages change with elevation, we see that there is a slightly steeper trend in the footwall compared to that of the hanging wall. But it is much easier to analyze this if we put together what is known as a pseudo-elevation plot. So what this does is, instead of trying to understand that there's a temperature difference between these 2 thermochronometers, we extrapolate that temperature difference into a elevation difference. So since the approximate closure temperature of the fission track and helium systems is about 30 degrees different, I calculated what 30 degrees would look like in a 32 degrees Celsius per kilometer geotherm. And we added that meterage onto these samples to acquire a pseudo elevation for the fission track. Note that we're normalizing everything to the apatite helium system. So anything with a closure temperature higher than that, we're going to be adding the elevation onto that. And now what these plots allow us to see is a more continuous trend of how these ages relate to each other. So rather than them being kind of side by side, we can actually see how they would connect to each other in a more cooling history sense. And what we can see is there is the steeper trend moving at about 0.3 kilometers per million year in the footwall compared to 0.1 kilometer per million year in the hanging wall. We can also see that increased spread in the ages resulting in a wider envelope seen in the hanging wall relative to that of the footwall. So based off of simply just the age elevation relationships we have acquired, it seems that there is an increased exhumation rate in the footwall relative to that of the hanging wall. Inputting this data into QD to produce some thermal history models, we see 2 different thermal histories produced on either fault block. So on the top, we have the footwall, which is the Monashee complex, and in the hanging wall is the Clackamas-Cudan, the upper unit. So from these thermal history models, here's each individual sample. These are the individual sample paths that were modeled and then put together into a single fault block cooling history envelope inside of these more bold lines. And the thermal history model for the footwall indicates that there was a rapid cooling episode of over 10 degrees Celsius per million year between 18 and 16 million years ago. Whereas in the hanging wall, there's an overall more protracted cooling history with two smaller cooling pulses at 20 million years and at 10 million years ago. However, they were much slower than the footwall, and they also produced just less cooling overall, whereas these cooled completely from the apatite partial annealing zone up above the helium partial retention zone. These cooling pulses were basically within these helium retention and annealing zones. So the thermal history models also indicate that the footwall and the hanging wall of the Columbia River Fault have experienced different cooling histories. So putting together a different exhumation history and a different cooling history, and seeing that the timing of these events is approximately the same, centering around 20 million years or so, I interpret this as evidence of reactivation of the Columbia River Fault, where the footwall of the fault was more rapidly exhumed, leading to increased cooling in the footwall relative to the hanging wall. Putting my data together with other published data from the Monashee complex, I can put together a three-stage cooling history for the Monashee complex, adding onto the history that was already previously described from thermochronology. And on the left here, we have the Monashee complex, and adding on other fission track data, as well as zircon, helium, and zircon fission track data, we can see this early core complex formation episode, which has already been described by previous studies. But adding on our data, we also have this new fault reactivation episode where we have another dive in ages. So just to explain again, this is another pseudo elevation plot. So these thermochronometers have all been normalized to the helium system. It's similar to the other one I showed you. Okay, so the previous data shows the original core complex formation, and now our new data shows this fault reactivation episode. Whereas when you look at the hanging wall, all the data kind of just comes together in more of a cloud-esque shape with a lot greater dispersion among the ages. Greater error in the ages is often correlated to slower cooling rates as well, for a variety of factors that complicate thermochronology. But I will say that the wide dispersion in ages in the hanging wall compared to the small dispersion in ages, as well as the steep cooling trends, are all indicators that the footwall has undergone rapid cooling, whereas the hanging wall has not. And the only way this is possible across this major fault is that there was motion across the Columbia River Fault. So there are some young ages that we've found in the area that I mentioned were from lower elevation. Previous studies have suggested that the glaciation starting in the Pliocene is the likely contributor, where valley deepening from glacial incision resulted in a final pulse of rapid cooling. However, that cooling was not enough to actually produce a cooling age, and resulted in these erroneous ages kind of between the timing of faulting and the timing of glaciation. That's the idea behind these young ages, that is. So when you take it all together, we have this three-stage cooling history for the Monashee complex. Core complex formation, a lull from about 40 to 20 million years ago, and then again from around 20 million years ago. But then after that, it seems that faulting has ended, or at least a measurable amount of faulting has ended. Now, is this the only place in southeastern Cordillera that has seen this reactivation? Or is this a more widespread feature that we need to investigate? To answer this question, I took data from elsewhere in the Cordillera outside of the Monashee complex to really look at if this is a more regionally occurring event. And I produced thermal history models for several different localities. So the only places I produced these thermal history models for were where we had samples along elevation profiles. So this means that I could actually input different elevation samples into a single model in QD to investigate how these areas were behaving kind of more as a fault block rather than individual samples with no spatial correlation. And this is why it's important that we have samples in these elevation profiles, because the sporadic age dating prior was not didn't carry enough information to actually investigate the timing of these faults. But putting together elevation profiles from pre-existing data and modeling it, we can see that in the footwalls of these normal faults, which have been shaded in gray, there is a rapid cooling episode at approximately 20 million years ago. Whereas outside of the footwalls of these outside of the footwalls in the hanging walls of these normal faults, there is a much more protracted slow cooling history. And this indicates that the footwalls have been cooled, whereas the hanging walls have not. And the only way this is possible is that these normal faults have been reactivated at about 20 million years ago to be rapidly cooling and exhuming these rocks. It's also worth noting that the foreland belt has not seen, let's see, this one. The foreland belt has not seen any cooling since the late Cretaceous, which is likely related to thrusting and everything related to mountain building. So east of the Rocky Mountain Trench, we have not seen really any kind of cooling history since late Cretaceous, and west of the Rocky Mountain Trench, we're only seeing pronounced cooling histories in the footwalls of these normal faults. So that begs the question, what is causing the reactivation of these normal faults in the Miocene? So the model that we propose is that the Shuswap domain is operating as a Miocene horsetail structure, operating off of the Rocky Mountain Trench as a main fault feature. Looking at tectonic data, GPS data about tectonic movements between the Pacific and North American plate, there is evidence that there was an increase in transtension as the Pacific plate motion vector rotated towards the northwest, as well as an increase in the plate motion at that time. So by moving into a more margin parallel motion, as well as an increase in plate motion, this resulted in an increase in transtensional stresses throughout the area. I have on these stress diagrams noted the rotation of the horizontal stresses as a result of this tectonic reconfiguration. And what this does is this rotation decreases the horizontal stress maximum that is being applied across this extensional corridor. Now, the reduction in this horizontal stress being applied allowed for an existing gravitational instability to further extend the upper crust in the area. This is the model proposed from Fraser et al. In 2021, where we have this gravitational anomaly existing in the Columbia Mountains. And I'm adding on to it by saying the rotation in the plate vectors allowed for this gravitational anomaly to further extend laterally. So a combination of both plate tectonic reconfiguration and a pre-existing gravitational instability were what allowed extension to reactivate in the Miocene. Now, this is not the only place that there seems to have been Miocene extension occurring, and for similar reasons. Looking to along the western margin at the Queen Charlotte Basin, there has been approximately 6 kilometers of subsidence in this basin since 20 million years ago, and it has been proposed that the existing gravitational instability of the thickened coast mountains allowed for the formation of this major extensional fault and the extension and subsidence of this basin. So coinciding at the same time, this plate tectonic reconfiguration allowed for an increase in transtension, and which was taken advantage of by these gravitational instabilities to allow for fault reactivation to occur and extension to occur throughout the southern Canadian Cordillera. So in summary, post-orogenic extension in the southeastern Cordillera has extended beyond the Eocene and into the Miocene. I showed this with evidence from specifically around Revelstoke, but then also extrapolating it to other areas in the southeastern Canadian Cordillera. We attribute this extension to being caused by a reconfiguration in the Pacific and North American plate tectonic shifts, which reduce the horizontal compressive stresses holding together this extensional corridor and allowing the gravitational instabilities to further extend the upper crust through brittle normal faulting. I would just like to thank everyone for listening to my talk. And of course, I would like to thank all the people involved in doing this research, particularly my supervisor, Ava. She really pushed this along, and I can't thank her enough. Also, Will Matthews for all the questions he answered for me, which was an endless list, as well as postdocs and students that helped me along the way, particularly Scott Jess, who trained me how to do all of these software the QD modeling and all that software stuff. Kelly Fraser and Ryan Greco for helping me out collect stuff in the field. And also my grad student compadres who kept me sane in the office. Our conversations are the only thing that got me through those 2 years, I will say. And finally, just want to thank NSERC and Geoscience BC for financially supporting me during this time. And of course, I would like to thank the CTG for granting me this prestigious award of the Best Master of Science thesis. It's very humbling, and I can't thank you enough for that. So thank you, and I'll be happy to field any questions you have.
Great. Thanks, Kade. That was, yeah, it's great work. It's very exciting to see, and you're definitely deserving of the prize. Do we have any questions from people in the audience? You can either type them into the chat or raise your hand.
Seems that Bayan has her hand up.
Bayan, yeah, feel free to unmute yourself and go ahead.
I think you had a struggle to pronounce my name, so please help with that. Actually, I was wondering, you mentioned about the Pliocene, the glacial erosion, like the youngest age, and I was wondering, you were finding those kind of younger age only in the low elevation, or there was also in the higher elevation, the youngest